Alright, ladies and gentlemen, this is how I believe protoplanetary disks are made. Today is September 10th, 2016. Saturn was a small impact between two small objects. The size and energy of the impact determines the size of the disk. So if there was a small impact and it happened outside of the Saturn, of the spherical body of Saturn, it'll conserve angular momentum and become rings. If there was a very large impact, like the one below, you'll have a very young star, like the Sun, or hotter and bigger than the Sun, younger than the Sun. And you have two large objects slamming into each other, you'll make a huge field of shrapnel. Those are called protoplanetary disks, debris disks, or circumstellar disks. Those are all the same things. They're basically rings around a star. Now, how this happens is very simple. You have an object orbiting another object. This is the companion, this is the host. As it orbits, it just, minds its own business, it's orbiting. And then an outside body from an outside source comes and flies over. No, I shouldn't say fly, but floats over and slams into that other object, and there's a huge impact. And would you guess it, since this is still going around the host star, it's going to conserve angular momentum, which means that material that caused the impact will become stellar shrapnel, and it will make a huge cloud of it. And it will just spread out all over the place and make a giant tail. And it will spread out in this direction, it'll spread out in this direction, and it will become thicker. I'll show that in the next paper here. But what I want people to keep in mind that it keeps its orbit and the majority of angular momentum. It's like if you have a large bullet and it's flying through the air and it gets hit by a smaller BB on the side. Well, that bullet is carrying so much angular momentum, not really carrying it, it's a conceptual thing, but it has so much angular momentum and mass that even if this BB were to hit it really, really hard, this round would still go forward. There's a video of that. I'll see if I can find it and link it to the bottom of this video. But if this object hits it, it's still going to go forward, no matter how fast this thing is going, because of the angular momentum of this object. But given that happens, there's going to still be some splattering around that object. Same goes for this impact and this impact, which is going to make a large field of shrapnel. And after that happens, it'll keep on going, and the field of shrapnel will just get wider and wider and wider and longer until it takes up the entire previous orbit. So you'll have this giant orbit of all this shrapnel. Basically, what it will be is an asteroid field. That's what you get, basically. And it stretches out in many orientations to conserve angular momentum. It just doesn't, it's not as simple as people think it is. But here's the beginning orbit. It goes from that to a wider orbit right there. So it stretches out this way. It goes to a smaller orbit. Orbit becomes narrower because some stuff falls inwards. It gets burned up by the host or keeps a nice tight orbit around its host. It gets thicker, so the shrapnel gets wider. And here's another orientation. I just flipped that onto its axis so you could see that I just turned this over just a little bit. So it gets thicker in this direction too, this direction. So you have this big disk thing. It becomes a protoplanetary disk or debris disk or circumstellar disk. It's all the same thing. And what I really want to stress to my listeners is that it gives a special feature of a new shrapnel field. A new shrapnel field, once that shrapnel field spreads out, if there were objects previously there in its path, those objects will clear out a path through the shrapnel. It'll blaze a trail like as if there were lawnmowers in a large field of tall grass. It'll just keep on going. The tiny shrapnel will get chewed up by those previously orbiting objects, which means there will be gaps in the disk. And those gaps were previously existing objects that just paved through that shrapnel field, and that's what scientists are looking at when they look at protoplanetary disks. They say, well, there's a planet forming there. No, what actually happened is that an object was destroyed, took up a large disk orientation, and previously existing objects just continually carved out their path through that, and they're not seeing planet formation. They're seeing a shrapnel field get carved out by previously existing objects. But there you go. And I just want to stress that if there's an impact large enough, it's going to create a huge field of shrapnel. It's just going to all over the place. And that shrapnel is going to continue going. And it's going to conserve angular momentum. It's going to become a giant disk. And that's what happens with objects that have rings. That's why all the gas giants have rings. It's because there was an object that had slammed into another one around it. Uranus has rings. Jupiter, Saturn, Neptune, they all have rings. It's because their gravitation is strong enough to hold on to that shrapnel after it was formed from a collision between two larger objects. But anyways, that's it, Baz. I hope this helps you out. It's very important to get the sequence of events right, because establishment, they have protoplanetary disks as somehow losing angular momentum and then becoming spherical objects. That's wrong. It's the spherical objects become disks. So you have spheres, okay, becoming disks as their angular momentum is lost. But you'll never have a disk becoming a sphere unless there's some mechanism to bring that material inwards. And as far as I know, the angular momentum problem is still yet to be solved, and it's basically something that's been known since the 1700s, but astronomers ignore it because they don't realize that planet formation is stellar evolution. All right, y'all, take it easy.